figures. Today we're going to be talking about 10.5 nets, cross sections, and solids of rotations. This is the last thing I taught you guys before we went on spring break, way back in March. So I'm just going to be covering this briefly. I'm going to be trying to go in depth when I can, but it's going to be very similar to what you guys covered right before we left. And of course, if you guys have further questions, always just let me know, stop in for office hours, or send me a quick email. So, what our learning target is I can determine nets of 3D figures, determine the shape of a cross-section, and rotate 2D figures around an axis to create 3D figures. So those are our goals for today. Let's go ahead and get started. So, first off, a net. A net is a diagram of the surfaces of a three-dimensional figure that can be folded down to form a three-dimensional figure. That can be folded to form a three-dimensional figure. To identify a three-dimensional figure from a net, look at the number of faces and the shape of each face. So the way that I think about a net is flattening out a box all the way down, breaking down the sides, laying it out flat on the ground, and that way you can actually see how you form the box itself. That's what I think about when I think of a net. I don't think of it so much as just taking it apart, but taking it apart completely and flattening it out as much as possible on the ground. And that way you can see every single face of the net. So that's what it is. So, complete each row of the table. Express the circumference of the cylinder as a multiple of pi. So if we deal with the cylinder, we're going to be dealing with pi. So if I look at this first one, we have this object over here, right here, and we need to list the type of solid it is, so we need to give this a name. We need to either draw an example or write an example if they don't give us one. We need to count the number of faces, and we need to create a net, which they give us on this one. So first off, let's go ahead and think about what type of solid this is. If I were to look at this solid, I see that two of the faces on opposite sides are the same. So these two can be our bases, or the top and the bottom can be our bases. So it doesn't matter which one you choose. But if I were to look at this, it would be a rectangular prism. So this is a rectangular prism, because it's a rectangle and it's a prism. And then I need to count the number of faces. So I can do that in two different ways. So the more difficult way is counting it on the actual 3D figure. So I have 1 and 2, the front and the back, 3 and 4, the top and the bottom, 5 and 6, the two sides. However, if I want to make this easier and I already have a net drawn, I can just count the net. 1, 2, 3, 4, 5, 6. So there are 6 faces on here. And faces are the pieces that are facing the outside, exactly as it says. So faces are facing the outside. We have 6 of those, 6 faces. All right. Next up, we have a triangular prism. So you guys can try this one on your own if you need to, or you can just give it a sec and I'll go through it. So if I draw a triangular prism, I start off by drawing 2 triangles, and then I just connect the corresponding parts. This last one I'll make dash because it's behind. So there's my example of the triangular prism. Now if I were to draw out the net, the first thing I'm going to do is I'm going to draw the bottom, that bottom part of the prism. From there I'm going to draw my 2 faces that are my bases. And then I need to think about what would happen with the other 2 sides. Well, if I were to lay them flat out, they would be right here. And there's our net for our triangular prism. So that's all you gotta do. All right, let's go ahead and try another. This time, we have a net and we have the number of faces. So the number of faces, it says, is a rectangle and 2 pairs of congruent isosceles triangles. So these 2 are a pair of isosceles congruent triangles, same with these 2 over here. So if I were to fold this all up, each of these points would meet at the very top, which would make this a pyramid. But let's go ahead and be more specific than just pyramid. If I look at the bottom of the pyramid, we have a rectangle, so this would be a rectangular pyramid. If I want to draw an example of this, I draw a rectangle. I'm going to kind of draw it sideways, kind of like a parallelogram. Then I'm going to put 1 point on the very top. From here, I just draw all of my lines to this point. And there's our rectangular pyramid. And that's it. All right, let's keep going. Next, we have a cylinder. So it says keep it in terms of pi. We don't really need to do anything with that right now. So if I look at this, our faces, well, we have 1, 2, 3 here, so we have 3 faces. If I were to draw a net, I'd draw 2 circles, the top and the bottom, and then they're connected by this whole thing that wraps around. So if I were to think about this as like a label on a can, if you were to go to your pantry right now and grab a can of anything and take the label off, you'll notice that that label will actually be a rectangle. So our wrappers on our labels are rectangles, so this would actually be the net of the cylinder. Of course, the length would be 2 pi r, which is the circumference of the circle. Here's the height, and then both of these are pi r squared. This is for the area, of course. So that's all we have to do for cylinders. All right. That's it for nets. Hopefully you can flatten out those shapes. Of course, if you have any questions, just let me know. In your homework, it should be mostly just matching and knowing which one goes with which. Next up, cross sections. So we talked about this before we left. Recall that a cross section is a region of a plane that intersects a solid figure. So I take a plane, and I treat that as my knife. If I cut a figure with that plane, and I take that figure apart, it should have 2 different pieces. So if I were to take this watermelon, for instance, and I always relate this back to Fruit Ninja, and I were to cut this watermelon, this is what my cross-section is. The cross-section is the part where the cut is made. So if I were to ask what the cross-section of this watermelon is, you'd tell me, hey, it's a circle. That shape is a circle on the edge here, so that's what it would be. Cross-sections will almost always be simple figures such as triangles, circles, and rectangles. So keep that in mind when you're going through these. You're most often not going to have one of these answers for them. And that's all we're looking for. So, describe the cross-section of each figure. Compare the dimensions of the cross-section to those of the figure. So if I were to take this plane and cut this cylinder right here, what is the shape? Well, it's a circle. And if I were to take this plane and cut it anywhere that's perpendicular to where I already cut it, we would notice that the cross-section does not change for parallel planes, no matter what. So that's a nice thing to know, that cross-sections will not change for us. What about this next one? Well, what shape is this? If I were to take this plane and cut it straight through the vertex, as we can see right here, and it's not going quite through the center, well, this shape would be a triangle. So it creates a triangle for us. The cross-section will not change dimensions if it is not moved from the vertex. So if I don't move this from the vertex, I were to just spin it around from this vertex point and, of course, keep it perpendicular, it will not change the cross-section. However, if I take it at an angle, it definitely will change the cross-section. So it determines on whether or not we're moving from that initial position, which will determine whether we are doing this correctly or not. Next, we have this shape right over here. Well, if we were to cut this shape out, we would end up with a rectangle. So the area of the cross-section would change depending on where is taken from the cross-section. So if I went straight through the center, that would give us the most area. But since I'm taking it not from the center, that will give us a little bit less of an area. So it all depends on where this cross-section is being taken from, on whether it'll be a lot or little. All right. That's it for cross-sections. Just remember, we're just playing Fruit Ninja, cutting the figure, seeing what shape comes out of it. Lastly, generating 3D dimensional figures using rotations. We can generate 3D figures by rotating a two-dimensional figure around an axis. Generally, it'll be the X or the Y axis. So, all we're doing here is we're taking objects and we're spinning them around in 3 dimensions. If we spin them around 360 degrees, that two-dimensional figure will suddenly become a 3-dimensional object. Now, along with this, we have a very important note here. If we rotate an object 360 degrees, that means a full circle. Well, then we're going to have circular shapes, because anything that's moving 360 degrees creates a circular shape. So anytime that we're making these 3D figures, more often than not, you're going to end up having a 3-dimensional shape because we're rotating it 360 degrees. Granted, later down the road, you'll be rotating on 90 degrees, 72 degrees, stuff like that, which will change what type of figure you're dealing with. Oftentimes, you'll still be dealing with pi because we are still rotating it, but just keep that in mind. It all depends on how much we're rotating. So, describe and sketch the figure that is generated by the rotation in three-dimensional space. Rotate the triangle around the the y-axis. What shape does it form? So if I were to take this figure, and I'm going to go ahead and just outline it here. We have this triangle, this right triangle, in fact. We see it's a right triangle there. If I were to rotate this around, and it were to go 360 degrees, I'd end up back at point C. However, A would have also rotated, and all parts of AC would have rotated, and made a cone for us. So we would have had a cone. Now, with this cone, we realize that BC is our radius, and AB is our height. So if AB is 8, our height is 8, and BC is 6, our radius is 6, what is the volume of the 3D shape? Well, volume is equal to 1/3, for a cone at least, pi r squared times height. And that'll give us 1/3 pi times our radius, which is 6, squared times 8. This will give us 36 divided by 3, that's 12, pi times 8, which will give us 96 pi centimeters cubed. So that is the volume of this 3D shape. If our radius is 6, our height is 8. Would the volume change if you rotated the triangle around the x-axis? So let's go ahead and see what would happen if that were the case. I'm going to do this in red. So there is where A would rotate all the way around. I'm actually going to change that point. Let's move it down a little bit further. So we rotate all the way around. And we have this red cone now. Now, automatically you should be thinking, that doesn't look like it's the same shape. Even if I were to rotate this new red cone 90 degrees and line it up, one's going to be much more flat than the other. Would that change the volume, though? Well, more than likely it would. Sometimes it may not in very rare circumstances. But yes, the volume would change. Let's go ahead and check that right now. If I want to see if the volume would change, I go ahead and I solve for this new volume. Again, I'm going to use the same exact measurements. But this time, my radius is 8. My radius is AB now. And my height is BC. So again, the 8 and the 6 switch spots. So now we have volume is equal to 1/3 pi times 8 squared times 6. Well, 6 divided by 3 is 2. 8 squared is 64. 2 times 64 gives us 128 pi centimeters cubed. So yes, the volumes are different. They did change. So the axis of rotation matters. It matters which axis you're rotating around. So next up we do have this rectangle here, and it says rotate the rectangle around the y-axis. What shape do you get? So I go ahead and I have this y-axis here. I have my x-axis. If I were to take this rectangle ABCD, and I were to rotate this around the y-axis, say I choose point D and I rotate it around 360 degrees. And I do the same with point C, 360 degrees. Well, what shape would this create? Well, if we assume that CD is also going around the edge here, then there should be an edge right over here. And we create a nice cylinder for us. So we'd have a cylinder with height equaling AB and our radius equaling BC / AD. So we now have our radius, we have our height. Next, if AB is 10, so our height is 10, and BC is 3, our radius is 3, what is the volume of the 3D object? So for a cylinder, we have volume is equal to pi r squared times height. In this case, our height is 10, our radius is 3. So we'd be left with pi times 3 squared times 10. Well, from here we follow PEMDAS. 3 squared gives us 9. 9 pi times 10 gives us 90 pi centimeters cubed. So that's the volume of this object, 90 pi centimeters cubed. All right, almost done. Lastly, What shape would you get if you rotated the circle around the y-axis? So again, we're going around the y-axis this time, and I have this circle here. So if I were to rotate this circle 360 degrees right back to the start, we'd notice that we'd have a bunch of circles going around, right? So there's an infinite amount of circles that are going around in the space to create a solid shape. Now, what shape would this create for us? Well, if you think about it, this is connecting at every single point. This would create a nice donut for us. So this has a donut shape. So it does matter where we're rotating this around. We're rotating around the y-axis, and this object is not on the y-axis. So there's the space that's created right in the center here. Now, if our shape was on the y-axis, I'll go ahead and draw a semicircle right here. And I were to rotate this semicircle around the y-axis, then of course it'd create a sphere for us. Same with a circle around the y-axis. If I were to rotate this 360 degrees, I would have a sphere as well. In fact, I'd only need to rotate the sphere 180 degrees. But regardless, it matters on where we're rotating it around. If I were to say, okay, we're going to rotate this circle around the line x equals 5, then this would definitely create a sphere for us. But we're not saying that. We're saying let's rotate it around the y-axis. And in doing so, it opens up the space, giving us an entirely new shape, a donut. So again, it matters a lot on where we're rotating from, what we're rotating about, and what shape we're dealing with. So just pay attention to that as you go through these types of questions. All right, so your homework is posted on Schoology. Make sure that you guys try that out. It's all ready for you. The more that you practice these, the better that you'll get at them. Stop by office hours or email me with any questions that you guys may have. If you need anything, please let me know. Other than that, take care, guys. I'll talk to you soon. Thank you.